Cool. Okay, so we've talked about how ds is equal to dq reversible per temperature based off the Carnot cycle, but this idea only occurs if you have, so this is equals only if this is all of the all of these cycles and the processes within the Carnot cycle are reversible. Reversible adiabatic, reversible isotherm, reversible adiabatic, reversible isotherm. If any one of those systems follow an irreversible path, this is no longer true. So ds is going to be greater than dq irreversible over T. And so the entropy will always be greater if any process has an irreversible step to it. Just one irreversible step is going to cause ds to be greater than dq irreversible over T. Okay, so now I want to talk about how for an isolated system, we're building towards the Clausius inequality, by the way. So for an isolated system, I have no change in heat with the outside or with the surroundings. So the system is completely isolated. And so if that's the case, if I have an isolated system, ds is going to be, but it's still an irreversible process, ds is going to be greater than 0. I'm also then going to have dq reversible minus some dq is going to be greater than 0. And so you can think about an irreversible process as the heat associated with the reversible process minus some amount of heat that's lost and not gained back to become a reversible process. And if you think about it this way, if so pressure volume, if that's my reversible process, if I'm going to get back the same amount of heat that I put in, I'm going to follow this path again, and I'm going to keep going back and forth on this path if it's a reversible process. If it's not a reversible process, I'm going to lose a little bit of heat energy and not gain it back. So that's that small amount that's been lost. Okay, so if that's the case, that means, well, actually, this will always be greater than or equal to 0. Sorry, that's an important point. And so for a finite change in an isolated system, this ds, so for a finite change, meaning I know how much ds has been changed, that becomes delta s is greater than 0. Okay, and likewise, dq reversible, make sure I get this right, per divided by temperature is greater than or equal, my notation is just awful, is greater than dq per T. Okay, so what I've done is I've taken this additional Q that I would have had if it had been a completely reversible process, and I've lost it now, and it's moved to the other side of this inequality, and I've divided by temperature to relate it to entropy. Okay, so now I've got dq reversible per T is greater than dq of the heat energy that I would have lost per temperature. Okay, so for an isolated system, you can assume that the delta S of the universe is going to be 0. So delta S universe is equal to delta S of my system plus delta S of the surroundings. Okay, and this equals 0 for an isolated and a reversible process. Okay, so so for an isolated system, delta S of the universe is going to be 0, which means that delta S of my system is equal to minus delta S of my surroundings. Okay, and so if this is the case, you can also say, so this is for an isolated reversible system, you can also say delta S of the universe is greater than 0 when you have at least one irreversible process occur within your system. And this leads us to the famous definition of the second law: the entropy of the universe of a spontaneous process increases. So if we define that the delta S of the universe is honestly, it's going to be the delta S of a spontaneous process increases for an irreversible process. It's equal to 0. A lot of cases as well. But for if the entropy of the universe of a spontaneous process increases. So delta S of the universe is greater than 0 for spontaneous. Delta S of the universe is equal to 0 when you've reached equilibrium. And then delta S of the universe is less than 0, means that your process is written backwards. So process is spontaneous in the opposite direction. And this originates from the idea that you're going to have, for an isolated system, your delta S is going to be increasing of your universe for an irreversible process. And if it's spontaneous, there is an irreversibility aspect of spontaneous processes. You won't have a spontaneous process that is reversible. Say that again. Because delta S of the universe is increasing, delta S of the universe is increasing because of the irreversibility aspect of one part of the cycle. If there's an irreversible aspect, the Clausius inequality comes in, and your delta S is going to be greater than 0 of the universe, and that's of the combined system and surroundings. Now, you might have a delta S of the system be less than 0, but your delta S of the surroundings, if this is negative, negative makes it a positive. Of an isolated system, that would make the delta S of the surroundings positive overall, or more positive, which would mean the whole thing is going to have this be greater, or sorry, it would mean that the delta S of the universe would still be negative because this quantity would be larger in magnitude than this one for an irreversible process. Okay, cool. So that's the Clausius inequality. The next videos are going to give an example of using the entropy in relation to heat.